All right. So I'm pretty amazed by this. China is very much into like taking care of their people while evening. So now they're going to have a gaming curfew for video games for minors. This is something caused by many, many Americans always say that pornography is bad for you, video games are bad for you, TV is bad for you. And remember there's a time when they were going to put a V chip in all the American televisions to block the violence for kids. But they never pushed too far in America because we have the First Amendment. But China doesn't have any First Amendment, so they're totally going to do it. You're not allowed to play at night anymore, and they're only allowed to play 90 minutes a day on weekdays and 3 hours on weekends. So that will be interesting because I know, anyway, and I don't know how you're going to enforce this, but anyway, maybe they'll, the next logical step, if you really care, is to force all the video games to have like a spy chip reporting back to the government or anyway, but I mean, I suppose, anyway, we'll see what happens. But that's in the spirit of China. They're very much into pushing people around for their own good, much more than America. Anyway, I don't know what you're talking about. Good. All right. So Uber. There was a Uber self-driving car that just plowed right into a woman, and now they're releasing why it did that. And it is pretty interesting. Now, I thought the whole point of AI was that it learned from real experience, but apparently this AI was never trained on people jaywalking. It only practiced on people walking in the crosswalk. So it doesn't know that people walk elsewhere. So it could not figure out what that thing was it saw that was not in a crosswalk. And they even report moment by moment what it thought. At 10 seconds before the crash, it started speeding up from 35 miles an hour because it passed into a faster zone. And then 6 seconds before the crash, 5 seconds before the crash, it classified this as a vehicle. There's something on the side of the road. It must be a vehicle, and it's not in my lane, so it doesn't matter. And then it flipped back and forth, seeking its other. I don't know what it is, but then back to a vehicle and other. And of course, it only thinks vehicles are going towards me or away from me in the lane. It doesn't think vehicles are going sideways across the road, and which would certainly be a bad AI model for Beijing, I must say. But anyway, so they now show what it did. It had no clue that it's possible for a human to walk across the road. So anyway, that's pretty interesting and in retrospect, pretty obvious. Just like a human, it only knows what it has experienced. So one statement about this is, well, you need to improve the data set you use to train your AI. Anyway, so 8chan has been down for a few months, 3 months, because Cloudflare blocked them. Now, and this article is like so many articles written by someone that doesn't know what they're talking about. Most articles are, and they claim Cloudflare was hosting them. Of course, Cloudflare doesn't host anybody. They just protected them. So they totally would, if Cloudflare denied service to them, they would stay up. They'd still be available somewhere, but I think their hosting providers also all kicked them out. Nobody will host them anywhere. So they claim, this article is unclear. They say they're back up, and then they say they're still talking about how to get back up. So I don't really quite get it. But anyway, they're planning to move to some kind of blockchain-based hosting so that nobody can take them down. And people talk about this a lot. If you could somehow distribute the hosting using a blockchain or something like that, then you'd become bulletproof. And people have talked about this a lot. All the models to actually make this work seem to be sort of half-baked and never really get too far. I know about 6 years ago, the US government started trying to arrest people in France because France legalized file sharing. So people in France would connect to French servers and download copies of American movies. And the US government said that since you went to a domain name like movies.fr and that went to an American DNS server, to resolve it, that means that traffic passed through American jurisdiction, and anything that uses the DNS system is subject to American law, and we can arrest anybody that uses domain names anywhere on the internet because they're all technically in America, which struck me as outrageous overreach, and it also struck the French that way. And a bunch of European people, led by, I think, Mikko Hyppönen from F-Secure, said, we're going to make an alternative DNS based on blockchains that does not pass through American servers because the Americans suck. And they tried to get people together to do that, and nobody really did. There's people trying to do it. Some other system besides DNS, because ultimately all DNS traffic pretty much does come to America to be resolved, and there are various reasons why that's not perfect. But anyway, they've got some plan to distribute the website on the blockchain so nobody can censor it. It'll be interesting to see how well that works. I think the only thing like this that works well is Tor. Tor is pretty good at putting up stuff that's hard to take down, although it can be taken down and has been taken down several times. But if it was really on a blockchain like Bitcoin, it would be really, really hard to take down. Anyway, of course, a lot of other fun things would happen. If you had a really offensive website on the blockchain, then everyone running a node would now own child pornography. And I think somebody did try putting child pornography in the Bitcoin blockchain just for this reason, because now everybody that runs a node would be committing a felony. And what are you going to do about that? And I think people just sort of have decided to like not worry about it, but it is a problem. Anyway, so this is the one. So Saudi Arabia had 3 people working for Twitter who were spying into accounts to find out what they were saying. Now, so everyone's getting very upset about this. And of course, they're sneaking spies. And I would assume this happens all the time. I know the US sneaks spies in everywhere. China sneaks spies in every company. They're leaking stuff back, and you catch them now and then. And the thing that, and of course, the employees sell things for money all the time. This just happened to one of the security companies. One of their employees was just selling data to someone so they could be spammed. Anyway, so it's the game where people are getting very upset about it. But I mean, the person who did this most egregiously was Mark Zuckerberg. He admitted that when he started Facebook, he didn't like the fact that some journalists wrote negative articles, so he manipulated the login system to reject everybody 3 times. So his failed passwords would have all their other passwords. And then he used those passwords to go into the journalist email accounts to see what they were saying about him. And he admitted all this publicly. And I was floored. I'm like, holy crap, he just admitted a pile of felonies. What's going to happen to him? And the answer is nothing. Nothing happens. Sort of like Donald Trump. If you just do it openly, apparently people are shunned to prosecute or something. Anyway, so we'll see what happens. But this is more there. Now, Airbnb, there was a Vice article that came out last week where somebody found a big conspiracy where you would go to an Airbnb and it would have these pictures that look great. And when you, just before you get there, they'll send you a message saying, gee, they shut that one down because the water heater broke or something. But I got another one that's bigger and better. And when you go there, it's like horrible. And then you can't get your money back and you can't reach the people. And when you look at the pictures, they're all fake. And she found that the same fake pictures were being used all over the country. There's some people that own a whole bunch of like horrible rundown houses with garbage furniture, and they're tricking people into going there. And then when you try to get your money back, you can't get it back. And anyway, so Airbnb is responding. They say they're going to verify all 7 million listings. They're going to make sure those houses really are as advertised, which seems like a really large undertaking. And I don't know if they can really do that. But anyway, this is, of course, the same thing with Uber and Lyft and Craigslist. These things where you're just buying some service or product from just a random amateur. Of course, some of those guys are scammers or selling junk. And how do you deal with that? Whereas if it was just a store, like a warehouse, like Amazon products directly from Amazon, then you would have somebody to sue and some quality control, and they could have a warranty team to replace it and stuff. But when you're just the middleman connecting people to each other, then some of them are going to do rotten things. And now you can argue about whether it's really your fault. Like Uber. Uber is claiming that they do not have to pay overtime benefits to their workers because they are not employees, because they're not essential to the business, because their business is not providing rides. Their business is just providing a network service to connect people who sell rides to other people. They're like just a newspaper, they say, and they have nothing to do with the actual rides. And they're therefore not responsible for treating the workers as employees. And if the workers do bad things, that's not their problem. That's an interesting argument, and it might work. Like if you publish those ads that you see at the news at the grocery store, this little flyer with ads in there, and then you buy something from there, you can't really sue the flyer. All they said was, this guy said he was selling you something, you bought it from him. It's not my problem if the purchase leads to something bad. Anyway, all right. So let's get to the official stuff here. So we're here at 127, and hopefully this thing is recording. Let me just make sure. It is, good, all right. So, all right, so we're going to talk about Windows Defense's protection mechanisms today, and there's several more classes still coming, and then I'll talk about some extra projects after we do this. So let's start with the protection mechanisms, and other things will come up as we proceed. So the protection mechanisms should be here, and there they are. All right, so let me make this relatively big so I can point around on it, and I see a chat message coming in. Is buffer overflow and string format bug the only way to take over RIP? No, I don't think so. You could also use structured exception handler exploits and heap overflows and there may be other things in certain code. There's no end of limitation. I mean, taking over RIP is essentially any remote code execution exploit, and there's a lot of them. There's, for example, direct command injection. So, but those are common ones, buffer overflow and string format. Another big one, really big, is dangling pointer. And I don't have a dangling pointer project. I haven't found a good one that fits in this format. But dangling pointers are actually a really big one, where you define a pointer to an object, and then you quit using it, but you forget to delete it. So it's still possible to inject data, and that data now goes to an area of memory that is being used for another purpose. So it amounts to a lot like a format string bug. You get the ability to write to memory, and you just have to find some memory that is used as a pointer, and you can take over the machine. So that's a good one. Anyway, so here's the protection. We're going to talk about the basic protection mechanisms that are used to protect Windows primarily, although the same things apply for Linux. The non-executable stack is the big one. See, back in the days of Windows XP and all the earlier versions of Windows, everybody was taking over things with the classic aleph null buffer overflow attack. That was the boss way to take over things, and the majority of exploits worked that way. And Microsoft finally got fed up with it, and Linux got fed up with it, and they turned on defenses. And the primary defenses they turned on are these stack defenses. First, they made the stack non-executable, so that even if you find an overflow and you can put code on the stack, it won't run. Then they put canaries at the end of the stack, so it will detect if you've overflowed the stack to such an extent that you're going to hit the stored instruction pointer. They put a canary there, so you'll hit that first, so they will know that has happened and refuse to attempt to return from a corrupted stack. And then they have a few other ones we'll talk about here: ideal stack layout, ASCII armored address space, and of course the one you know about, address space layout randomization, where you just move code randomly in memory. Those are the three big ones that greatly limited the power of buffer overflows. So it went from being like 90% of all Windows exploits to like 10% of all Windows exploits after this, because they became much harder to do. There are ways to do them still, but it's much more difficult, and it made a whole generation of malware obsolete, and that was the main point. Anyway, so then there's heap protections, which are getting better and better in each version of Windows, and some structured exception handler protections, which are also getting better and better in each version of Windows. So there's two kinds of protection mechanisms. There's general protection mechanisms which harden the operating system so that even if you run old code on the new OS, you're safer. And that's nice. Of course, that's much more protected because a lot of companies have old legacy code they're running. But of course, there's a limit to how much you can do there. There's two problems. And the first thing, if there's bugs in the code, you might not be able to stop it with a defense in the OS. And the other thing is, when you turn on protection measures in the OS, you'll often break legacy code. For example, when data execution prevention broke a bunch of code, and I think address space layout randomization broke a bunch of code. So you often have to turn these things off for legacy code because they're not compiled in a way that can cooperate with these defenses. So anyway, but these general protection mechanisms do make you a whole lot safer when it works. It's sort of like companies that don't patch their code. Instead, they buy like a web application firewall and try to stop the attacks on the way. And this has the advantage that you don't have to rewrite your code, but it's not as strong a defense, of course, because it just is a challenge to the attacker to modify the code to sneak past your defense, and then it's still vulnerable behind there. Of course, the entire world is currently in this situation because all of our hardware processors are vulnerable to all the Spectre and Meltdown flaws, which cannot be patched. So we are all in the position of using known vulnerable hardware and having software defenses around it that we know are not perfect. And various people are getting upset about this and trying to design the next generation of processor. And so far, we're just waiting for that to happen. So here is some C code, for example. So if I define an integer variable and a string here, 80 characters long, and then another integer, then in a standard stack layout, it will just put them in the order I define them. And down here's the saved return address. So if the buffer is overflowed, I can overflow into this variable. And then if I overflow even further, I can overflow the saved EVP, and then I hit the saved return address. And this is the classic aleph null type buffer overflow that we've been doing a lot of in this class. So a non-executable stack means that even if you put code on the stack, it will not run. And this is enabled by default in all modern operating systems. So you can still overwrite the return address. So let's talk about this. If you inject code and it won't run, you can still overwrite this address. And when it returns, it'll go to that different address. So you have not made it impossible to redirect execution to another part of memory. What you made it impossible to do is to run code that you injected. Now, I saw a chat message come in. Zoom showing only my Google, not my code. Oh, thank you. Let me check. Thank you for telling me. All right, let's see. I must be sharing the wrong thing. Oh, I thought I was sharing I said I'm sharing my desktop. Let me try switch to something else and then switch back to sharing the whole desktop. Is it okay now? I just went back to switching to desktop. Good, let me know if, good. I don't want you guys to get ripped off over there. So here's what I've got. I've got a classic buffer overflow. The string overflows to here, and I can hit the EBP and the return address. And that will happen even if I have data execution prevention turned on. All DEP does is mean if I inject executable code here, it won't run. But I can still change the address, and it will work, because that's not an execution. Just taking that address and putting it in the EIP to resume actually does not involve executing code I put in there. So that's important to know. Non-executable STAP does not prevent you from exploiting the machine. It just prevents you from adding any new code. So what you do is you return to code that's already there. And there's a bunch of ways to do this. The general point, this is called return-oriented programming. You return to code that somebody else put in there that is executable, that Microsoft put there or that the developer put there. So you can return to a data section, for example. You might have a data section where you can put shellcode, which is executable. That would be nice. Then you return not to the stack, but to that data section, and then you can run code you put there. If you do have some ability to write to memory that is executable. But return to libc is the more common thing. This is where you can run any C library function by just jumping to the address where the C library function is, or to one of the pointers that points to it. So you can run system or WinExec on Windows or something else. The only problem here is, of course, you can't inject more than 1 0. You can only inject 1 null at the end of the string, and that'll end your exploit. So if the code is in addresses that have zeros in them, you're going to have trouble injecting those addresses. Return to string copy is a special case of this. String copy is a C library function. So you could put your executable code on the stack and then go to string copy and copy it to another location and then run it there using the C string copy to do that. So that's one way to do it. So again, here's before the overflow. So you would overflow and you would put string copy here, and then you would put the other parameters you need on the stack. So the destination address and the source address and wherever you want to go after that. And now it will copy data based on this and then jump to that address when it's done. That's what you're doing here. So, all right. Then you can return to getS. This is kind of fun too. This will run getS, which takes code from the console and puts it in memory. And so you can then, if you have the ability to put standard in code, to type something, command line, it'll go into memory and then you can execute it. That's the game here. Again, you have a pointer to getS, and then you have some parameters here that are passed to the function. You can return to code. This is a general plan. We've done some of this where you jump to code that's in the application. You find anything in the exe, in the DIL, in the libraries. You just find any code that does anything good. And then you can do change, return to code, which is what you do to build something piece by piece. So you can fix the stack pointer after each return with pop, pop, pop return, or you can return into functions using calling conventions. And I'll show you this exactly in the project I'm going to demonstrate later. A student asked a question yesterday about this, and I couldn't find the project. There was a project missing from this class. I just put it in today, 309, where you do this. Somehow it was omitted this semester, so I put it back in, and I'll show you how it works. And then return to syscall. You find code fragments and chain them together, and therefore you can execute a syscall, any kind of syscall you want to run something, which would be a kernel routine at that point. And you can return to the text section of the binary where the program's code lives. That's just another way to talk about return to code. This is where you go to the code that the developer put there. And I see another chat message. That was me. I solved that takeout. Good. I'm glad to hear you solved it. Okay, good. And but anyway, it did point out to me there was a missing project, so I'm glad I put that back in. And then jump to the procedure linkage table. We talked about this. This is normally how I get to library C. It's also how your program does it. There's a procedure linkage table, which is pointers to libc. You could jump directly to a libc function, or you can go through the procedure linkage table, which is how the compiled code does it. Either one of those is fine, whichever one you can get to. You can go to a dynamic linker resolver, and this will use library functions to find, so you can actually use functions that are not used by the target binary. they're not in the procedure linkage table, but you can get them elsewhere. If you have been taking, I don't remember how I put it in this class. I might have put it in this class. I think it is. I talked about this. This is what we did in this one, server-side template injection. This way, you're exploiting a Python-based development web development environment, web production environment, and you can actually insert Python libraries that the developer did not import. You can go to the import function and add other libraries so you can exploit them. And you can do that here with C also. You can go to this location and you can then use library functions that were not compiled into this function, which is pretty awesome. So the non-executable stack did not stop any of these exploits. All it did was mean we can't inject new code. We just have to use the code that's already there. So that's the thing to do. Okay, then there's stack defenses. You can see them in Visual Studio C++, and there's projects you've probably already done on the list about this. So if you make assembly code here, in order to, now one thing about Microsoft's stack cookies, which are the canaries, another word for them at the end of the stack frame, Microsoft Visual Studio does not put them in every routine. It only puts them in routines that have buffers. So you have to write something that has a buffer with at least 5 characters in it, or 5 words anyway, and then it will decide this one is possibly at risk, and it will turn on the stack cookie. So if you do that and compile this thing, you can now right, I'm just going to print out an address in data, address in stack, address on the heap. I just create various objects and print out the addresses of them so you can see them. And if you compile this thing with protections in modern Windows, that means you don't turn anything off. This EHSC is just the standard compile switches. So if you compile this thing, then the defenses will be here. And it'll have the stack here, and here's addresses intact. So, and if you run it over and over, you'll see that text and data don't change, but the stack and the heap do change. And this is the important thing about Microsoft's address-based layout randomization. Not everything is randomized. I don't know why. I guess they made a decision that not everything is very risky and it's too expensive to randomize everything. So, all right. And that's why return-oriented programming is possible. At first, I was very confused by this. The text section does not move, even with address-based randomization turned on. So you can find the code the developer put there. I don't know why Microsoft did that. If Microsoft really randomized everything, then return-oriented programming would be essentially impossible because there wouldn't be anywhere to jump where you'll find anything you know. It would all be just randomized, but not everything is randomized. All right, so you can compile without an address-based randomization by turning on dynamic base to no at the linker, and then you'll find that nothing changes. Anyway, but the stack cookie is the only thing that changes now. Every time you restart the program, it re-randomizes the stack cookie, which is that this is the stack. So you have the variables you put here, and the stored return pointer is down here, 409 EA1. And this cookie is random. So if I overflow the string and try to hit it, I'll alter that, and the return function from that subroutine will never happen. So we did that. We talked about that before, and I've got some Kahoots. Let me bring up the browser that allows me to use Kahoot. My Brave browser is awesome, but it won't let me use Kahoot. And then I cannot, because it cannot handle the Google OAuth login. I have to figure out what the problem is someday, but in the meantime, I just work around by using the older browser for this. So they will try to trick me into paying for something, and I will eventually get to my favorites, and those should include 127, chapter 14A. Okay. While that is loading, I will try and get a, oh, good. This is ready. All right. Won't move though, there it now moves, all right. So, good. Oh, by the way, Ron told me that the quiz engine is down, and it seems to be down right now. So if you haven't done the quizzes today, you won't be able to until they come back up. It's a free service, and it appears to be broken. So If you're late on the quizzes, you should not lose any points for a while until that thing comes back up. All right. And I don't hear any sound, which is, I guess it's just not playing the music yet. I'll wait a few more seconds. Let's see, I've got 8 people online and maybe 6 or 7 in the room. So I should be able to get a little higher here. Good, I think we got at least one more person joining in the room. This thing won't move for some reason. All right, there we go. Wow, the browser is really like freezing up on me. Anyway. All right, I'll give it a few more seconds. Anybody still joining? No screams of protest? All right. So, shellcode placed on the heap by buffered data processing. Looks like for some reason the music really is gone. I think it might be this. There we go. All right, that's return to data. All right. All right, which one uses DIL code that the target executable did not load, which is pretty awesome. Okay, let's return to DIL resolve. Good. All right. Which one puts shellcode on the stack but executes it elsewhere? Return to string copy. It's on the stack, so it's a parameter which is then copied to another location by string copy. All right. And which one reads shellcode from standard input? Okay, that's return to gets. All right. So let me record the winners. 3 for Vin and 3 for WITB, who I know who that is, and 3 for Anton, which I think is a real name. All right. So let's get back to here. All right. So here's another general defense measure. Every memory segment should be write or execute, but never both. This is to end several offenses. Something I used to do in the 8-bit assembly days a lot was write self-modifying code, where the code, I'd have like a write store to an absolute address, and then I would calculate the address and just write it right into the instruction. So I could create things that with a variable location that were not available. And that seemed great to me, but this is considered a horrible practice because you can't even read the code or print it out. And so that's one thing you don't allow here. You don't allow anybody to modify something that's executable. And this also means that nothing read from the user can be stored in memory that's executable because that's writable. So any writable area should not be executable. That's the plan. Now, the Windows operating system does not prevent you from allocating a region that is both writable and executable, but compilers and such like Visual Studio will not create them by default. So normally code doesn't have them. Linux had a version of this called PAX, which was considered quite secure, but was considered too slow to become popular. Microsoft uses the NX bit, also called data execution prevention, and this limits executables. It makes it possible to mark an area of memory non-executable, adding permissions to it. All right, and so here's the game. Now change ret code will still work, of course, because you can find areas that are executable but not writable, and you can jump to them and use the code that's already there without modifying it. So returning to code still works. And of course, you can create memory regions that have both of these things turned on, but they won't be there by default. So a normal stack overflow that goes on the stack will not be writable and executable by default. All right, and by the way, of course, the fundamental problem with all Windows is that all these things are optional features and you can turn them off with API calls. So if you gain any limited ability to execute code on the machine, you can make an API call to turn off the defenses. And that is, of course, the boss way to do it. And this is analogous to, there's a lot of malware that will get on your machine and turn off the antivirus, which is the kind of thing you might want to do, turn off the firewall, that sort of thing. This makes sense, but of course you have to have some degree to execute things. Here's one thing: set information process. This will turn off the protection, turn off write or execute. You can change a specific memory region. Virtual protect is what sets the protection features for memory locations, so you can turn off this feature for certain memory locations. And that's the game, by calling these functions. And we'll see virtual protect again later when we do the ROP chain. You can also do them one at a time. First make it writable and write to it, then make it unwritable and executable and now execute it if you can change the protections during program flow. So, you know, there's always a technique, and you can use virtual alloc to allocate a new region of memory, and you can give it permissions, both writable and executable. So, you know, any of these are possible if you have some degree of execution available. So then there's the stack data protection. This is where most of the attention was faced, because for 10 or 15 years, everybody was doing these buffer overflows on the stack. And so they were really motivated to fix that. Now, after Microsoft nailed this down, they started moving to other areas to secure it. But this is where most of the attention went in development of, say, Vista. So Canaries is the first one. StackGuard and ProPolice were versions of this, also called stack smashing protection, which is what you'll see in Linux. These are just various ways to put a canary on the stack that will notice if you're doing an overflow. So instead of having just variables and then a saved return address, you put a canary here. So if they start overflowing things, remember I said right at the beginning, when the very first overflow we did, we would go from one variable into another variable and no further. And I said this kind of overflow is in fact very hard to stop. And this will not stop that kind of overflow, but that kind of overflow usually doesn't give you code execution. It's not very likely that one of these other variables is ultimately used as a pointer to execute. But if you want to get to the return address, which is the boss way to get it, you're never going to get there because this canary's in the way. And when you modify the canary, then you'll get busted, unless, of course, you are fortunate enough to have an information disclosure vulnerability that allows you to read the canary and put the right value back there, but normally you don't have that. So the first canary people put in was a null canary, always null, because the idea was you couldn't inject that. The null would terminate your strings. So then they decided nulls are not always impossible to input. There are some of the projects you have in this class where you're putting in hex values and nulls are okay. So they made the terminator canary, which is null and line feed and FF and 0D. Those are all the possible things that terminate strings in other fields. The idea was one of those things will terminate your string so you can't inject that number. So that was the idea. Then the most popular thing these days is just a random canary. All right, another thing you can do is ideal stack layout. Instead of putting the variables on the stack in the order in which the coder assigns them, it rearranges them to try to make it safer. Because of course, if I define an integer and a string and another string and some floating point variables, I don't really care where they are on the stack. I just have to be somewhere. And so it tries to move them all by putting all the strings at the end. So here's the ideal stack layout. It will put all the buffers right at the end, the idea being that if you overflow them, you'll hit the canary right away before you hit anything else. So now there's nothing to exploit here. You either don't overflow or you hit the canary. You don't have this opportunity that I was talking about to hit other variables, which might give you some ability to control the machine. But if you have multiple strings, it can't put them all at the end, so you still might have one string leaking into the next string, and it can't protect you from that. All right. But the problem is they make compromises, and that's why I mentioned this before. If you make a routine that only has like a few integer variables and no strings, it will not have this defense, because Microsoft's compiler will decide it doesn't need to bother putting a canary on that because there's no chance of exploiting it. So, you know, it's like all defenses, it doesn't put every possible defense in. It carefully chooses defenses to stop what the most active attacks are. All right, so we talked about this. By the way, if you define C++ structures, which are data structures, it cannot rearrange those, because then you specify exactly the structure. There must be a string here and then a pointer here and then another string, and it can't move them around because that's the structure of C++. The whole point of it is you define a data structure. So that's a thing that there are limitations in what you can do here. All right, here's more. If you allocate buffers, they have to be on top of the stack frame. And of course, even if you do have the ideal stack layout, there might be something after the buffer and it might be useful. So in principle, some degree of exploitation is still possible. Now here's another trick, ASCII armored address space. All you do is load all shared libraries in low memory. So all the addresses start with 0. This is pretty good. It's awfully hard to inject an address. All the addresses will have zeros in it. So that will stop a string-based exploits, which is the most common type. There may be cases, like a few of the projects here, where you can actually inject nulls and they get in, but most of the time, nulls are not allowed, and this would work. So if you want to execute this command that adds a new user account to the system, you will have to inject one null here, but you can still make one call because of little endian. The point is, if it's little endian, then you have the little bytes of the address, and the high order byte of 0 comes at the end, so you can still put in one of these addresses right at the end of your exploit, with the null being what terminates it. So it doesn't stop you from doing it, it just stops you from doing it more than once. So if you find a way to exploit the machine with only one system call, you can still do that, and that's what this does. One system call, which then runs bin shell and gives you some information. Anyway, that's the game here. So here's defeating ASCII armored address space. I put in an injection which has an address with the 0 at the end. And so I'm able to inject right up to the 0, and that address will execute one record starting with 0. All right, so that's the game. All right. And there is some code that is still not relocated even with ASCII armored address space. So all these defenses are imperfect, but they were designed to stop the generation of malware that existed at that time. And they caused people to have to rewrite their attacks to add more tricks into the attack to get past them, which is all you can ever accomplish. So I got another Kahoot. Yeah, I don't know where you'd send Trump. He's definitely an American product. I don't think anybody else wants him. This is what Snowden, my Snowden led. He couldn't find anybody that wanted him. They could get the hell out of here. China didn't want him. The only people who would take him is Russia. And Assange had the same problem. Nobody on Earth wanted him. Nobody would take him but Ecuador. Yeah, he wanted to go to China. He tried going lots of places. If the NSA is mad at you, you don't have very many friends on Earth. I mean, who wants you? Yep, there's only a few. And Russia seems to have won by putting Trump in. Now we're all pro-Putin. That's why one thing Nancy Pelosi said, a lot of people said, if you analyze what's going on, everything Trump does, all this crazy stuff always ends with Putin. He really just seems like, I can't understand why he's mad about the impeachment. He's not going to get impeached. He could just turn off the television and ignore it. That's what Bill Clinton did. He's got $1 billion. He's the president. He can't be impeached. He could just turn off the television and stop worrying about it. But somehow he doesn't. Anyway, somehow he cares if people say mean things on TV. That really bothers him. Anyway, I would just turn off the TV and do whatever I wanted. Anyway. So, which one puts shared code in low memory addresses? I see a chat coming in. I'll look at it after this. That's ASCII armored address space. I don't really know why they call it that. And I see a chat message, dementia. Well, I thought of that, but I think most people have given up on that. Trump isn't stupid. He's not, at first, the way he talked to me, I just all think his mind was not working at all. But it's not that simple. He's just very strange. He has weird priorities. It's very hard to understand what he's doing. He has very different goals than most of us would understand. Anyway, so which one causes code to stop when it hits enough? The common issue in the projects. Okay, that's the non-executable stack. That's how you can detect it. Inject some NOPs and jump there. And if the NOP won't run, the only thing that can possibly cause that is a non-executable stack. And that's a test I often do early on to decide what I've got. All right. Which one uses carriage return and end of file characters? That's the terminator canary. Every possible terminator they could think of, so you're unlikely to be able to inject that. Which one protects the return value, but not the stack frame point? Yeah, it was one of those early ones, stack guard. I don't remember quite what the stack frame pointer is, but I remember saying that was a limitation of it, why it wasn't considered so good. Anyway, Vin is in here twice, and M. Dot and Ken are new, so I know who M. Dot is. And Ken is a real name, so we're doing pretty well at keeping track of who won. Okay, so there's another section of these, and then I just want to say a few things about the project. All right, so then there's ASLR. We talked about a good old friend, nice simple idea. Every time a process launches, it picks a random location to launch it in, so you never know where you are. Now, of course, processes run with a virtual address. They all think they're running at 400,000 anyway, so they don't really care where they really are if they're executed with position independent executables. So now technically, this means performance suffers to some small amount but in fact, it can be a lot on 32-bit code because it means a register is permanently holding the offset. So one of your registers is used up. And one of the problems with 32-bit code is there really aren't enough registers. So you spend a lot of time shuffling things back and forth. In 64-bit machines, there are a lot more registers, so you can have one hogged up and it doesn't slow you down as much. Anyway, here's ways to defeat it. You can do return to gets, where it will now get data from the user, and you can tell it what address to store it at, so you know right where it is. Now, of course, this means return to gets has to be findable, so that library has to not be jerking around. All right, you can also find information disclosure vulnerabilities. This was a big thing in Windows XP. EBX, I think, always had a code that would tell you where you are. So if you can find something that tells you something address, then you can use that to find out where you are. That's one way to deal with it. Linuxgate.so is another thing. This was a table of pointers that was always in a fixed location. So you find something that's not randomized. Of course, the other problem is Microsoft's randomization implementation was not random enough. Some versions of it had as little as 8 bits of entropy, so there were only 256 possible locations, and some of them had 12 bits of entropy, and both of those mean that if you can try to exploit a few hundred times, you'll just get lucky. Anyway, another thing you can find is that even if things are randomized, they move relative to each other. So once you find one guess that works, you can make other guesses that work. These are limitations of the system. And of course, another one, which I'm not seeing here, but is heap spray, which doesn't seem to work in modern browsers because they changed the way Internet Explorer stores strings, but you would run JavaScript to just make thousands of copies of your exploit and then jump randomly. You fill up all the memory you can reach with copies of your exploit, and then it doesn't matter where it is. Anyway, all right. So there are ways to find addresses. If you can escalate, then you can actually, in Linux machines, do proc PID maps. You can find the memory map. The memory map is stored in proxy. You can find out where things are. I've done this by brute forcing 16-bit values. If it's not randomized enough, you can do it. Even a 24-bit value can be brute forced if you're willing to try your exploit 16 million times, and that might be possible. Right, format string exploits leak information. They'll reveal addresses. They'll totally tell you where things are. If you just look on the stack, you'll find pointers to things. There are IPC calls that leak memory addresses. And if you have multi-threaded applications, the address space has to be the same for all threads in a process. So you might be able to open multiple connections and touch multiple threads and get more chances to make the brute forcing faster. This is essentially what Dan Kaminsky did in 2008. The original point of DNS security was that you had a 16-bit random value protecting DNS requests. So when you made a DNS request, it labeled it with a random 16-bit value, and when you got the response, it would look at the 16-bit value, so you could not spoof that value. And Dan Kaminsky found a way to send 500 values in one request. So he could actually brute force a 16-bit number much faster than anybody thought he could. So that's the kind of thing here. If you have multi-threads, you might be able to do more than one guess at the same time. Anyway, then there's fork. A lot of Unix processes work by forking. In fact, early Linux distributions, there was one process that started the machine called init, and every other process was a fork of that. Fork is a common system call that just makes a second copy of the currently running process, and now they both go forward. But fork doesn't re-randomize the memory layout. The two processes remain connected, so that's a problem. And you may have other processes that are therefore connected to the first one and give you more things to attack. And then there's heap protection. So originally there was all buffer overflows. So Microsoft put in all these defenses to stop buffer overflows. So people moved to structured exception handler, Dagwood pointer, and heap attacks. And then Microsoft started the blue hat contest. So they got the attackers to come build the defenses, and the heap attacks got much more difficult. So the original heap problem was with the old normal heap, you just have nodes, chunks of data, and they have a forward and reverse pointer. So it goes to the next one and the previous one. And if you delete this one in the middle here, then you have to revise this pointer to point to this one and revise this one to point back to that one. But if you look at this, if I was able to do an overflow, then it tries to write here to point back there, and its information about where it's going comes from here. So the end result is you control a single write operation from overflowing this node. When it tries to fix the pointers, it ends up writing data, and you control the value and the location of that data. So this is the simple heap overflow exploit. So one thing is safe on link. Before freeing a chunk, it checks to make sure it's accurate. This is something Cisco routers implemented, something called check heaps. There's a process every 2 seconds that just walks the heap. It just starts at the beginning of the heap and goes next, 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 next to the end, and then back, 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 back. And if that fails, it reboots the router, trashing everything, say, all right, something's wrong. We'll not tolerate that condition. And this safe on link does something similar. It checks to make sure that the forward and back pointers are okay before freeing a chunk. All right, and it's implemented ever since XP Service Pack 2. In all modern operating systems. The problem is not all heap operations are protected by safe on link, and there's this thing called the Maleficarium online, and it's this lists all these complicated heap attacks, which are pretty hard to understand, but it's a whole series of other heap exploits you can do on Windows primarily. I think it's mostly on Windows. I tried to read it, it was too dense, and I didn't bother trying to make projects out of it or anything, but then there's unsafe unlinking, because this test is not perfect. It doesn't really walk the heap and make sure it's intact. It just checks that certain pointers go to certain places, so you can in fact overwrite them in a way that will still pass the test. So that's one way to do it. One common thing people do in heap exploits is they overwrite the pointers in a way that make it look like the heap is just empty, because that's pretty easy to do, and then it still passes the test as still being valid. All right, now, so Microsoft has this thing called a look-aside list for the heap, which I think is to handle heap fragmentation. It's not just a single linked list. It has another table here so it can like take the chunks and reorganize them to defrag them to make the heap more efficient. And so anyway, there's various ways to do this, but they took away the look-aside lists in Windows Vista and switched to something called low fragmentation heap. Microsoft heaps are much more complicated than Linux heaps. You can still do heap attacks, but reading the details of them can really give you a headache. Anyway, heap cookies are now in Windows XP to search an 8-bit random cookie in each header, which sounds good, but it's only 8 bits. I don't know why Microsoft keeps doing this. Why do you put an 8-bit value and then pretend I can't brute force an 8-bit value? But anyway, that's what they did. There's heap cookies. Now they made it 8 random bytes in Windows Vista, which is more like it. Brute forcing 64 bits is essentially impossible. You'll never be able to try that many times. So that's a good idea. Windows 8 added a whole bunch more heap protections, heap handle protection, and fast fail and guard pages, just a bunch of more stuff. And this is all from Microsoft Blue Hat contest. They give people bug bounty rewards for developing an attack, and they give them more rewards for developing a fix to patch that attack, and the patches got much better. All right, here's even more of them. Pool cookies and safe unlinking and an on-page pool. And I don't really know what they all do. Microsoft has a lot of defenses to stop all these attacks, and they're constantly adding more. Much improved randomization. And with the modern processors, have hardware random number generators, and the Microsoft operating system uses them. Some people have the feeling that the random number hardware random number generator has been poisoned by the NSA and it's not really random. Microsoft, of course, does not worry about that because they're totally embedded with the government like AT&T, and they wouldn't care if that did happen. Your Linux fanatics will often refuse to use the hardware number generator because they assume it's been poisoned by the government, although nobody can prove it. And that's why, deciding if something is really random is a problem. Here's the Dilbert about it. If you ask it and you get 999,999, you still don't know if that's random. That could be random. How do you know? How many guesses? There's no way to really know if something's random. Anyway, all right, and that's the issue. They cannot really audit it. So it is a matter of faith whether you think the hardware generator is any good or not. Most people would just use it because it's better than the previous techniques, like using the clock or something. But if you're super worried about stopping the NSA from spying on you, may God have mercy on you. You can't hide from the NSA. I wouldn't even bother trying. But anyway, so Windows 10 adds even more defenses to stop these things. Just a lot of them to try to stop firmware boots. Some of the Windows now have secure boot, which requires signed firmware for updates, and even signed operating systems when they boot up, like an iPad and an iPhone. iPads and iPhones have no rootkits because it won't even boot up unless the kernel is signed by Apple, and it verifies that during signature. So you can't change one bit in the kernel or it won't boot up. Microsoft put that in one platform, which is Windows 8 on ARM or something, which nobody ever used. But they talk, it is an option on some hardwares. I think it might be in some version of Windows 10 now. That's the game. They can stop rootkits. There's just a lot more defenses Microsoft has added. And we've seen Smart Screen. This is the one that got people real upset. So if you open a browser, Internet Explorer or Edge on Windows 10 and surf, you'll see it sending all the URLs to Microsoft. And everybody freaked out about privacy invasion. That's Smart Screen. It's checking an online repository to see if those are known bad links to block them. Anyway, they have a lot of these things. And Microsoft removed the nastiest browser extensions like ActiveX and browser helper objects that were being used for malware. They took a lot of the defenses away. So OpenBSD has defenses too, and FreeBSD. They got rid of the old KMalloc and switched to mmap, which is better. So no two chunks can ever be adjacent, and now an overflow can't hit the pointers on the next chunk so easily. And there's more heap exploits. You can overflow these control structures and hit them, but it's getting hard. Everybody's making the heap more complicated and more secure. So these older generation exploits go away and you keep having more and more complicated ones. And then there's the structured exception handler. You got a project where we hit the structured exception handler and then cause an exception to take over the machine instead of using the return address. And Microsoft has put a bunch of structured exception handlers. Now this is, it used to be that when you go in the handler, one of the registers has an address that's useful. So they zeroed that out. And you can't put the exception handler on the stack, so Stack Overflows won't get it. And now there's a thing called Safe SEH, and this uses a whitelist of permitted exception handlers, so you can't put strange addresses in the exception handler list. It won't take them. This gets rid of trampoline attacks. And there's more of these. If you have a memory section not compiled this way, there are some protections in line. Here's EEREAP is an exploitation tool, and PDEST is one that freezes a process, and SEH Inspector. These are attack tools just for structured exception handler attacks. So, there's quite a lot of these. The war goes on. The attacks you've learned here are the simpler ones. There's a whole lot of advanced stuff constantly changing. Anyway, I got a few Kahoots about that, and then I just want to talk a bit about a couple projects here. So I see we're right on time. So we are at 14C. All right. This should be good. One great thing about this website, which I've imitated, is you don't have to make an account and log in and have a password or anything. I really like that. I did it from CTF Games. This is a good idea. Just don't even collect any data. Then you don't have to handle it, store it, and all that crap. Of course, it means you can impersonate people and use a fake name and have no defense against that, but that's an acceptable situation. This is how 4chan works. Nobody has an account. You just post things. It's all anonymous. I'll wait a few seconds and see if the 9th person is coming back. Apparently not. We will charge ahead. All right. So, which one bypasses ASLR by letting you specify where the code goes? Gets reads data from the keyboard and puts it to the address you specify. So now you know where it is. All right. Which one puts function pointers in a predictable location? That was Linuxgate. It put a list of pointers that didn't move, so it kind of defeats the point of address space layout randomization. Which one may have been poisoned by the NSA? Well, yeah, I suppose everything is a good answer, but there's one where the issue came up. But yes, I mean, the NSA may have poisoned the air. It might be full of microscopic bots going in your lungs, recording everything back. How do you know? There, that was the random number generator is the one. And that, of course, by the way, is not complete fantasy because they did poison 3 or 4 known random number generators. They poisoned ones used to make cryptographic keys and got caught several times. So they do have a history of poisoning the random number generators. All right, how many guesses will it take to find 2 random 8-bit values? $65,000. It takes 256 to guess one 8-bit value. And for the second one, you got to get 256 times 256. So 65,000 guesses, and you will have a pretty good chance of guessing both of those values. All right. So Humpty Trumpty, is that you? Who's that?
Let's do Fort Trump right here.
It's someone online. It is Vin. Okay, good. All right, thank you. So that means Vin won all 3 times, which is good for him. And Ken won twice. And somebody else here, Rich. Okay, good. Rich is a real name too. All right, so I got the records. So I don't think I'll bother doing live demos of these, but I do want to talk about the projects. I made some new machines because a lot of students with new machines were having weird problems. And I wondered if there was a fundamental problem with the Google Cloud or something, but I think there isn't because I made brand new machines here and they're working pretty well. The one thing I found that worked right away with my brand new machines, let me go here, is that I was able to ping back and forth right away. Now, I'm able to ping my Linux machine from Windows, which is what should happen. If I do IP address, my Linux machine is, whoa, what is this? That's right, I hit something by accident. All right. Go away. All right, so my Linux machine is 10.128.02, and I can ping it from Windows. 10.128.02. This is what Ron couldn't do last night. I don't know any reason for this, because you're very unlikely to have a firewall turned on your Linux machine. And even if there is a firewall on your Windows machine, it doesn't affect outgoing traffic. So you should be able to ping Linux from Windows. Now, to ping Windows from Linux is harder because the Windows firewall will block it. And but what I found before was even a fresh machine, if I turn off the firewall, I can ping. So here, I think that's the 10.166.02. Let me see if I can get to the, come on, stop messing with me, and get to the scroll bar. All right. Okay, 10.166.02. Now, I wasn't able to do that until I turned off the Windows firewall, but then I was able to do that. But what I found, which is the same thing that happened to Carla a while ago, is after doing that, even if I ran Vuln server, which I might as well do here in the debugger, I would run the Vuln server either inside or outside the debugger, and then run and run until I get the, if I can make my window the right size so I can get there. There, now you can see in the corner it is running. And now if I try to connect to that address with Netcat, what she found, and I've seen it before, right now it worked. I got the header. But when I first took a fresh machine and put on Bowne server and ran it, I did not connect. I could ping, but I could not connect on 9999. This seems to be true for like the last month on new Windows machines. I don't know why. And the solution that works, I do not know why, but the solution is to install Nmap and Wireshark, which I did to try to diagnose the problem. And after you do that, it works. And the reason I think is because Nmap and Wireshark install extra network drivers so that Linux-based code can access the drivers. And I think one of those, like npcap drivers, some of those drivers apparently interoperate better with this old Bowne server code. So Microsoft has updated their networking junk, and installing old programs turns on some old features. Anyway, what I did was install both of those things and then restart the machine. And when I did that, it still didn't work because restarting the machine turns the firewall back on. But if you put on both of those things, restart the machine, and then turn off the firewall again, now it works. So I had to do all that to get it to work. So it's kind of annoying. And I think I added to the first project, Bowne server, troubleshooting tips about this. This is very common. I was working with YKang last night for hours on another project. Many projects take many hours of debugging, and that's what the real education is. In the real world, you spend most of your life debugging stuff. If you expect like the manual to work or anything, you'll just have to get over that. Nothing ever really works. There's always weird complications. Anyway, so that's what I wanted to say about that. And I wanted to say a little bit about the new project, new to us this, which was missing, which is this one, 309. I was surprised. This was missing from class. This is an important project. There are two that go together. 308 is where you exploit vulnerable server. And if you remember in 308, we run this vulnerable server and we found a Stack Overflow and exploited it, but we turned off data execution prevention. So the way we exploited it this time was we put code on the stack and ran it. And that's fine, but that won't work very much these days. That's only for old operating systems, the ones that have turned off this defense. So this is the one where you turn it back on. You run Bowne server and you turn non-executable code back on. So once you've got an exploit running, and you're hitting the IP, now you can test code execution on the stack. And like I say, you now just inject NOPs. And when you perform your attack, it will, all right, it'll show an int3. If you can go through the NOPs and hit the int, then you have code execution turned on, which is what happened here. So now you turn on data execution prevention. You go into the advanced system properties and you turn on DEP for all programs except the ones listed below, and then restart the machine. And now when you run the same attack again, it doesn't get to the int3, it hits the NOP and stops. That's, like I say, if you can't do a NOP, the only possible explanation is data execution prevention. Obviously, that area of memory is not executable because there's no possible reason why it could not execute on NOP, except that nothing is executable there. So the solution is to use a ROP chain. And let me see what the chat is. Right. Installing Nmap didn't help me, but eventually realized that Windows had defined the network as public and turn off. Yes, you have to turn off the firewall for all the types of networks too. That's true. That's a good point. Yes, I always turn off the firewall for all the options because Microsoft does move the network from public to private and stuff and give you a headache. Yes, yes, it is. It's all harder than it should be. Yes. Anyway, these are good things to know. Anyway, so here's the ROP chain. So a ROP chain does not execute any code. What you do, you make a ROP chain with Mona. There's a Mona command down here that will make a ROP chain, ROP generator finished. And so it's going to have just a series of things here. And if you look at this, this is going to run Microsoft DILs. So there's one coming below. We save the log someplace and look at it in Notepad. And you can see this is virtual protect. Remember these methods we talked about in the lecture. There's virtual protect to change the protection levels of a memory section, and virtual allocate to allocate a new section. And Mona will generate ROP chains that call those Microsoft calls. So this mesh will go to virtual protect, and all this sets the memory so it will turn off the protection. And here's an alternative chain. These are ways to do it. So you find a ROP chain, and these things have different success rates on different versions of Windows. And so the thing, I think this one here, I vaguely remember the reason I was holding it back. I think I had trouble doing this on the latest versions of Windows. You might have better luck doing this on 2008, although I did get it to work on 2016 at one time. That might be why I had this thing missing from your projects. I vaguely recall there's something annoying about it. But anyway, this is the project. You can give it a shot. I made it extra credit because you may have difficulty. You may have to use the old version of Windows. But you get a ROP chain, and then you add it to the stack. So you put that. Mona will generate Python code, which makes the ROP chain, and you can put it in here. I'm just getting a funny feeling this may not work on Windows Server 2016. That might be why I had it removed from your projects. And I think I was hunting through and I found that all these things really only work on that old 2008 machine. So be warned, this is extra credit and there are problems with it. But anyway, that's what ROP chains are, and you can see how they go. The point of a ROP chain is you just inject a whole bunch of addresses on the stack, no code, and those addresses build your exploit. These things are on the way out, in my opinion. Microsoft is having more and more defenses against them to stop you from doing this. And the latest one is all the DILs will only let you enter the functions at the assigned entry point. You're not allowed to jump just a couple of instructions before the end. So you can't do this anymore with DIL code. And so, you know, Microsoft is aware of this and trying to put in defenses. And I think modern versions of Windows do have it so that these Moina-generated ROP chains don't work anymore. Anyway, so be aware of that. And I think I saw another chat message come through. These chats show up in the recording. I don't think they do. It's a good question. I think they do not. All right. Anyway, so the last thing I wanted to tell you is probably a good thing for people who may be behind. I added a whole bunch of extra credit to here on a different topic, which is good, clean fun. I got interested in Go. So I put this link here to Go the Wrong Way. I'm going to do this at B-Side San Francisco if they approve it, which I imagine they will, and all over the place. And so far, it's over 300 points of projects. I used to have a thing called Violent Python, and Python is going away, Python 2.7, and people are saying Python's over, you should all use Go. So I said, how hard would it be to use Go? And the answer is, it's pretty easy to use Go. Go is a compiled language like C, but it's supposedly a lot safer than C, and it's very easy to write like Python. So I just have a whole bunch of projects here. So you can use a Linux cloud server. You can, in principle, install Go on any OS, but I just use a Linux cloud server because, in my experience, this sort of thing always works better on Linux. And so you can make code here that does things. It's very easy. You can just install Go. You just have to execute a few commands here. This downloads the tarball and installs Go. And this junk sets all the parameters so the operating system can find Go. And now you can make Hello World. One thing that is a real good thing, why I like this, you have to get used to modern coding techniques. In the modern world, you don't just make a file and feed it into GCC. You have to make a directory and have various files because every project is a tree-structured directory with many components. So in Go, you make a directory, in my project, with the name of your app here, and then in that folder, you put your source code in a certain folder. That's what it expects. It wants you to put things in a proper tree-structured directory. So then you put in your code, and here's just Hello World. And then you compile it with Go install in the folder name, and it goes in there and expects a certain structure. So this is the way all modern programming languages work. So now you get Hello World. And Go is kind of like C, but a little different. Format printf is like C's printf. You have to have a main function. You have to import all the libraries you're going to use, just like you have to include standard IO here. So when you use something and you can't find it, you have to Google and find out what the name of the library is and put it in there. So there's Hello World, and here's a port scanner. So you need net, format, and string convert. Now I go from I to 65535. Now I format the integer from a 64-bit integer, which I think what is default what they are, and then to turn it into a string. And now it took this number and turned it into a string. This turned it into a string, so I can put it here. And now it's going to add that to this. So this is going to be 127.0.0.1 port. So this is going to scan my local system for all TCP ports, and that is really fast. One good thing is it's a compiled language, of course. So this will scan all 65,000 ports and tell you what's open on your local machine, which on my machine was 22 and 60. It'll be 22 on all of them because we're using SSH. I had 60 open because I was using this for the SSDT project. And the SSDT project, you open port 60 to run your server. Then you can make a banner grabber, which is really just a few lines again, and off you go. So these projects all follow the standard format where you've got several things you do, where it gives you complete instructions, and then there's a bunch of challenges where you have to scan some servers. You get an error message for scanning something here, and now you got challenges. Find a service somewhere in these 30 ports, do port knocking. When you connect to this port, it's going to send you a message that includes the next port to connect to, and you have to connect to that one within 3 seconds or it will hang up. So you have to write a string parser that will read this message and pick the port number out of it. And then the port knocking 2, here you've got a big paragraph and it puts the port you need in a random place in here. So you have to find it, and it's not always in the same place. And then I've got a bunch more here. This one here, you do HTTP requests. And I was actually the new one here is Caesar Cipher I got going. These are all ones I did in Python. But here I thought this was pretty fun. I learned how to do file IO in Go. And I made Caesar Cipher modified images. If you just take images, move all the bytes forward a few, they become totally unprintable. So there's image, you do some ciphertext with the key and without the key, and then you do some files. Reading files is actually pretty awesome. Just one line. In IoT read file will read the whole contents of the file and put it in data. You can do this in Python too, of course, but it's kind of nice. Now you got it in data. Now you can process it byte by byte. The only thing that really held me up for about a day was understanding there are not arrays in Go. There are things called slices. I don't know why. And they store everything in a goofy way. Strings are very annoying. They don't use 8-bit characters or 16-bit characters. They use something called runes, which I think always 32 bits. And getting back to ASCII and Unicode is kind of a pain, and getting back to bytes is kind of a pain, but I got used to it. And so now you see I make out is bytes, I read the data, and then I explicitly turn it into bytes before doing operations. This held me back for a while. But anyway, you can specify, I want to treat this 1 byte at a time and do ordinary byte calculations by using the byte data type. So it took me a lot of Googling to figure it out, but in the end, you can do it in simple ways. So now you can do byte arithmetic and move things around. So I've got that, and I've got XOR encryption in Go. I'm planning to add AES, and then I'm going to add steganography because you can totally read an image. You can modify it by bits, so you can totally do steganographic changes. So I'm going to keep making more of these. This is working pretty well, and I think Go will be my new go-to language to solve general problems, and like CTFs and everything. Python is kind of old and dying. Python 3 is available, but Python 3 is very annoying. And I don't think there's any reason to put up with all the annoyance of learning the details of Python 3. You should just learn Go, because Go is much faster. And Python 3 has very similar irritating issues about Unicode and the storage of bytes and stuff. And I don't really see any reason to learn that garbage when I can just learn the way Go does it instead. So anyway, it turns out that Microsoft 16-bit Unicode is famously a bad idea. When I did this one here for password hashes, I had very great difficulty making Microsoft password hashes in Go, because Microsoft does not hash this word password in ASCII. It hashes it in 16-bit Unicode, which means each byte is followed by a null byte. And I could not find, in hours of Googling, any way to convert Go data to that structure. And I found out, in fact, about 5 or 10 years ago, they figured out that this is a terrible idea, because even 16 bits is not enough for all the languages you need, like Chinese and Japanese and Arabic. So limiting yourself to 16 turned out to be a disaster. So there's a more general thing that goes up to 64 bits, which is what Go uses. And it doesn't bother with these halfway primitive broken systems. And there's no way to get back to them. So I finally found a super lame workaround. This is a brutal hack, which is there's my brutal hack. I just manually add the null byte after each character. And that will do it. I don't even attempt to store it in Unicode. I just store bytes and feed in the zeros myself. Anyway, but it was interesting to see. And that is because, that's why I think might as well skip over Python 3 and go to Go. Go has the most modern version of everything. And you might as well get to the modern world, especially with these international languages. Another thing that's happening in a lot of CTFs and a lot of projects, that I haven't done yet is an increasing number of projects have like Chinese characters and Japanese characters and names. The Splunk projects, the Splunk second CTF has a bunch of challenges where you have to like take a URL in Chinese and query for it. I didn't put them in my version of it, but we should start getting used to that, using weird foreign languages you don't know. That's the modern world. We should be able to do more of that. I know I did a CTF in, I think, Vietnam, and they didn't want to make it specific to their language. And they didn't want to give Americans a disadvantage. So they compromised by putting everything in Hebrew so that everybody was lost. And I didn't get too far on that one, but there was a website and every button was in Hebrew and all the documentation was in Hebrew. And they said, well, we might as well have a fair playing field. Now the Chinese, the Vietnamese, the Arabics, and the Americans all can't read this stuff. So anyway, but they're right. We should start getting used to that. Americans think everything is in English, but it's not. So anyway, all right. Anyway, any questions or anything? All right, well, I'll stop the share and I'll stick around here and help anybody that wants help. And I see a chat message coming in. Okay, might want to edit the instructions for 308 that tell you to turn off the firewall. Oh, yes, thank you. I'll make a note of that. You do not have to turn the firewall off for private networks. Okay, good. Thank you for telling me. Let me make a note of that. ED 308, turn off the firewall entirely. Thank you. Good. Okay, anything else? Okay, I'm going to stop the share. I'll stay around in the classroom to help anybody who wants to work here. All right.